Welcome, ladies and gentlemen. We are now looking at continuity for section 1.3. This is set 2. And during these two problems I'm going to show you, we're going to be using the definition of continuity. Without the definition of continuity, we can't prove continuity. So this is the foundation that you're going to be using as you move into calculus. This is very important. So you must know and remember the definition of continuity from this point on, just like you know your name, because there are three conditions that must be met in order for a function to be continuous. So let's move right into the definition of continuity, and let's see what it says. A function f is continuous at a when three conditions are satisfied, and a stands for the point for which we're looking. First condition, f is defined at a. That is, a is in the domain of f, so that f of a is a real number. Well, in this case, a is the input, and what it's saying here, you put a, that value, into the function, work it out, you get an output value, and it's a real number. So if you put this value into the function, work it out, and a number comes out, then it's defined because you got a number out of that. That's all number one is saying. So you do substitution. You take that value, substitute it in place of x, do the orders of operations. If you get a numerical value, then you know that the function is defined. It exists at that point. So if it passes step 1, then we move on to step 2. And in this case, the next step is that as x approaches that value of a, does the limit exist? So as these values get microscopically close to a, and they get so close that in this case you would need an electron microscope to see the distance as those values are getting closer to a, to see the distance between that value and the point that's getting closer and closer to that. Is this function arriving at a number? Does it exist? So that's condition 2 that we'll be looking at. If it passes that condition, then in this case the next step is to check to see, well, is the limit approaching where the function is defined? So for example, let's say that a is equal to 2. We put a into this function and 5 came out. Well, at this point we know that f of 2 is equal to 5. Then let's say that we take a look at the limit, and both the left and right hand limits as they approach get closer and closer and closer to 2. The limit of that function also approaches 5. Oh, well, in this case it passed the second test. We're getting a limit, and now we come down to 3, and in this case the limit has the same value as when we actually put a into the function, work it out, and get 5 out. So if this passes the test, then we know definitely the function is continuous, because now the limit is also equal to the function when we actually put a into it. So these are the three conditions that we will be using of the definition of continuity to determine whether a function is continuous or not at a particular point. So once again, you must know the definition of continuity as you know your name. Let's get ready to move on and take a look at the first problem. Thank you. Now here is problem 1, and we're given this function, and we're asked to determine if this function is continuous at where x is equal to 0. So that is what we're asked to do now. So we're given the function x squared plus 5x divided by x squared minus 5x, and we want to determine, well, is this function continuous at x equals 0? Well, from the definition of continuity, we have to use step 1. We must first see, well, is this function defined at x equals 0? So let's read. We must determine if f of x is defined when x is equal to 0. In other words, when we substitute x equals 0 into the function, does f of x produce a real number output? Well, we're going to use substitution. substitute x equals 0 directly into the function. And here's what we get. When we put 0 into the function as shown here as f of 0, we now have 0 plus 5 times 0 over 0 minus 5 times 0. We end up with 0 divided by 0. Well, 0 divided by 0 is an undefined form. So this function is undefined when x is equal to 0. So f of x is not defined when x is equal to 0. Therefore, these three dots mean therefore. Therefore, f of x is discontinuous at x equals 0. So it did not pass step 1. But now we're going to still see if we can graph this. So we must analyze the limits to determine how can we go about graphing this. So we already know that it's discontinuous, and to determine on what type of discontinuity is this. So we're going to move on to step 2, and that will allow us to analyze the function further and to determine, well, what type of discontinuity is this. So let's get ready to move on to the next page. Now we are at step 2. We must determine if the limit of f of x as x begins to approach 0 exists. To do this, we must analyze the left-hand limit as the values of x approach 0 from the left, and we must analyze the right-hand limit as the x values approach 0 from the right, as demonstrated here in this simplified drawing of the number line. Here we have 0, and our values approaching 0 from the right, and then we have our values that are approaching 0 from the left. Notice the signs. It's negative here on the left because left of 0 is negative, and to the right it's positive because to the right of 0 is positive. So in this case, if I'm coming in from the right, I'm coming in from the positive numbers. If I'm coming in from the left, I'm coming in from the negative numbers. We cannot, and once again, we cannot use the original function because it becomes an undefined function as the x values become microscopically close to 0. One more time. We cannot use the original function because it becomes an undefined function as the x values become microscopically close to 0. So once again, here is the given original function. F of x equals x squared plus 5x divided by x squared minus 5x. Let's go to the next page. Now we are at step 2. So here is the given original function, x squared plus 5x divided by x squared minus 5x. As we look at the original function, we see that we can factor out an x from the numerator and the denominator because the highest power that we can factor out from either term is x to the first power. That is the highest power that we can factor out. So when we do factor out the x, we now have f of x equals x times x plus 5 in the numerator. And in the denominator, we have x times x minus 5 in the denominator. Notice that the x's divide into one another. They are common factors. So the x's are common factors in the numerator and the denominator. So those common factors, they divide into one another. So they divide out. So when these numbers divide into each other, we're now left with f of x equals x plus 5 divided by x minus 5. The resulting function is a factored and simplified form of the original equation. So we're still at step 2. We can now analyze the left-hand and right-hand limits of the transformed version of the original function. Let's take a look. So right now we're going to look at the left-hand limit. This little negative sign means as the numbers approach 0 from the left. So we have that the limit of x plus 5 divided by x minus 5 as those values approach 0 from the left. Well, in this case, because they're going to be so microscopically close to 0, in this case when we're analyzing a function, we can now just substitute 0 directly into the expression. So when we do so, we have 0 plus 5 divided by 0 minus 5. That's equal to 5 divided by negative 5. That's equal to 1. So we now know that the limit of x plus 5 divided by x minus 5, as these values approach 0 from the left, they're approaching negative 1. And in mathematics, we're allowed to say that the limit is equal to negative 1, even though we know that it might not actually touch it, but it is equal to that negative 1. It's like a barrier. It can't go beyond that. So in this case, again, the limit of that function, the simplified function, not the original one, as the values approach 0 from the left, is equal to negative 1. Now let's analyze and evaluate the simplified version of the original function as these values approach 0 from the right. That is what this little plus sign to the right of 0 represents. That now we're looking at those values as they come into 0 from the right side. So in this case, once again, we're allowed to just directly substitute 0 into the expression. As we do the work, we end up with 5 divided by negative 5, which is equal to negative 1. And lo and behold, we see here that the left-hand limit is equal to negative 1, and the right-hand limit is also equal to negative 1. So now we discovered that the left-hand limit and the right-hand limit, they are both equal. Now in this case, since the right and left-hand limits are the same, these three dots mean therefore we can now say that the limit of f of x as x approaches 0 is equal to negative 1. Therefore the limit of f of x exists. Now in order for a limit to exist as it's approaching a point, if it's approaching a point, it cannot have two different limits at the same time. So if it's approaching a point and it has two different limits at the same time, then it does not exist. We're still on step 2. This is a removable discontinuity, or there is a removable discontinuity at 0, negative 1, because the original function, and notice I have underlined here original, because the original function is undefined when x is equal to 0. So let me read that one more time. So from our analysis, there is a removable discontinuity at the point 0, negative 1. Because the original function, we cannot forget about the original function, because the original function here controls everything in this case. And we were looking at the original function, and we saw that when we put 0 into the original function, we end up with 0 divided by 0, and that's undefined. So in this case, that point 0, negative 1 is going to be a removable discontinuity. So once again, there is a removable discontinuity at 0, negative 1, because the original function is undefined when x is equal to 0. Well, now it doesn't make any sense to go on to step 3, because in step 1, f is undefined. And in this case, we know that it has a limit, and in this case, it's a negative 1, and negative 1 cannot equal to an undefined function. So therefore, once again, step 3 shows us that because the limit is not equal to f of x, because f of x is undefined, therefore it's discontinuous at that value. So now the supplemental steps, which are Algebra 2 prerequisites, is how do we go about graphing this function? Let's go through it in the step-by-step process. How do I go about graphing this function? Here is the process, step by step, and I'm going to slow down so you can follow. In step 1, we want to determine, does the function have a y-intercept? In this case, does it cross the y-axis? So the minute I say y-intercept, you should be thinking x is equal to 0, because on the y-axis, x is always equal to 0. So, is there a y-intercept? Well, to determine a y-intercept, let x equal 0. We will use the factored simplified form of f of x. And that simplified form is f of x equals x plus 5 divided by x minus 5. Substitute x equals 0 into the function. So here we are in this line, and we directly substituted 0 into that function. We now have 5 divided by negative 5, which equals negative 1. So it does have a y-intercept, and it occurs at 0, negative 1. So when x equals 0 is substituted into our factored simplified form of f of x, the output, or our y value, is negative 1. So the y-intercept occurs at 0, negative 1. How to graph? Please remember that when x is equal to 0 is substituted into the original function. Once again, we're back to the original function. The original is undefined at x equals 0. Even though we get a value for the factored simplified form of f of x, we always must go back to the original function, because that is what we're actually trying to graph. So in the original function, we have to remember that when x is equal to 0, the original function is undefined. So we have that the point 0, negative 1 is the point of discontinuity. 0, negative 1 is the point of discontinuity. It will appear as an open hole of the graph. And we now know again that this is a removable discontinuity. Going on. Next step in graphing a function to getting the information that we need, is there an x-intercept? The next thing we want to know, does this graph cross the x-axis? So we've already discovered that the graph is going to cross the y-axis because we got a coordinate value. So now, is there an x-intercept? Well, what do we do? To determine if there is an x-intercept, let f of x equal 0. Now please remember that f of x is just function notation for y. We could also write that y is equal to f of x, which is equal to 0. So whenever we want to determine an x-intercept, we automatically should say, I know the y values must be 0 on the x-axis. So this is the reason why we set f of x equal to 0, because that's just function notation for y. So let f of x equal 0 in the factored and simplified version of f of x. So here we go. We have x plus 5 divided by x minus 5 equals f of x. In place of f of x, we substitute 0, and then we move on to solve. We now have x plus 5 divided by x minus 5 equals 0. Cross multiplying by the expression in the denominator, we have x plus 5 equals x minus 5 times 0. Continuing on with step 2. So now we're going to solve the equation x plus 5 is equal to 0. So we add negative 5 to both sides to get the x by itself. The 5's on the left side of the equal sign cancel. So we have x is equal to negative 5. There is an x-intercept at negative 5, 0. Now let's move on to step 3, of trying to gather information to be able to actually graph this function? Well, at step 3, once again, we're using the simplified version of f of x to determine if there is a vertical asymptote. So now we want to determine, is there a vertical asymptote? Meaning, is there a value of x to where that function is not defined, and that vertical line now breaks that graph up into 2 distinct areas. When we look at f of x equals x plus 5 divided by x minus 5, we must take the expression in the denominator, which is x minus 5, and set it equal to 0. Why do we do that? Because we know that if we have 0 in the denominator, we cannot divide by 0. The function is undefined. So we take x minus 5 equals 0. When we solve the equation, we get x is equal to 5. Well, what does that mean? Well, continuing on, x is equal to 5 is a vertical asymptote because it makes the denominator equal to 0. A function is undefined when there is a value that makes the denominator equal to 0. We cannot divide by 0. Division by 0 is undefined. Now we want to determine the behavior of f of x as it approaches the vertical asymptote of x equals 5. So in this case, it should have been written, we want to determine the behavior of f of x as the x values of that function approach the value x equals 5 from the left and from the right. So we're looking at the x values. What's happening to the behavior of that function as the x values approach 5 from the left and from the right? Well, looking at our expressions in the denominator and the numerator, when we put in numbers that are on the left side of 5, the expression x plus 5 will be greater than 0. In this case, the expression x minus 5 will be less than 0. When we put values into the 2 expressions that are above 5, for the first one we have x plus 5. When we put a value in to this expression of a number that's greater than 5, x plus 5 will be greater than 0. And if we use any number to the right of 5 and substitute that into the expression x minus 5, x minus 5 will be greater than 0. Continuing on, as x approaches 5 from the left, x plus 5 is positive, x minus 5 is negative. So we have a positive divided by a negative is equal to a negative. Now, as the values of x approach 5 from the left, we now see that that function is approaching negative infinity. Why? Well, we already saw why the signs came out that way. But remember that as we get closer and closer to 5, the difference between that number and negative 5 gets smaller and smaller. So for example, if I put 4.9999999 into this function, I'm going to be left with 0.99999. And as the denominator continues to get smaller and smaller and smaller, as we divide by smaller and smaller numbers, the quotient, the result of that division, is getting humongously big, and it's approaching such a massively large number. It's called infinity because we just don't know how large that is. It just continues on. So as the values of x approach 5, from the left, x plus 5 divided by x minus 5 approaches negative infinity. As x approaches 5 from the right, x plus 5 is greater than 0. x minus 5 is greater than 0. So we have positive divided by positive is positive. So here's what we know now. That as the x values approach 5 from the right, x plus 5 divided by x minus 5, that function begins to approach positive infinity. Moving on to step 4. Using the factored simplified version of f of x, we will determine if there is a horizontal asymptote. To determine a horizontal asymptote, we allow x to approach either positive or negative infinity. So once again, we're going to use the factored simplified version of f of x, which is f of x equals x plus 5 divided by x minus 5. So if we keep this factored simplified version the way it is and allow x to begin to approach positive or negative infinity, we end up with plus or minus infinity divided by infinity. That's undefined because no one knows how large infinity is, so we can't do the division. And that is why it's undefined, because we don't know what infinity is. So as a result of the undefined term or function above, we must divide each term of the numerator and the denominator by x. And here's why we can do that. As long as the powers are the same, in this case, the power of x in the numerator is to the first power, the power of x in the denominator is to the first power, and we want to convert that to a simpler form or something that we believe we can work with. As long as the highest power, the leading term, and the highest power in the numerator is equal to the highest power in the denominator, then you just divide each term by that power of x. So once again, in both the numerator and the denominator, the power of those two leading terms, the x, is the same, and that's the rule. And in this case as well, if the power in the denominator is greater than the power in the numerator, then we know that in this case, as x approaches plus or minus infinity, that the limit is going to approach 0, which we'll get into some later time. So moving on. So as a result of the undefined term or function above, we must divide each term of the numerator and the denominator by x. And here's what we do. So x divided by x plus 5 divided by x in the numerator, and the denominator, we have x divided by x minus 5 divided by x. And as we simplify these expressions in both the top and bottom, we now have 1 plus 5 divided by x in the numerator, and we have 1 minus 5 over x in the denominator. So we have these two expressions, 1 plus 5 over x in the numerator, and we have 1 minus 5 over x in the denominator. So continuing on now, we now take the limit of this expression as x approaches plus or minus infinity. So the limit of 1 plus 5 over x, which is being divided by 1 minus 5 over x, as x begins to grow larger and larger and larger and larger. So as x approaches plus or minus infinity, 5 over x is approaching 0. So after the 6th or 7th decimal place, this really does not affect the outcome anymore because it's so small we can just get rid of it. So as x grows larger and larger and larger, 5 divided by x is quickly getting closer and closer to 0. So when we begin to take the limit of this expression, we just cross off the 5 over x because they approach 0. Because they're approaching 0, we now have 1 divided by 1, which is equal to 1. So as these terms, 5 over x, begin to grow smaller and smaller, we now know that the limit is approaching 1 because after, like I said, the 4th, even the 5th decimal place, That's insignificant. We don't need it anymore. We can just drop it. So the limit of this is actually equal to 1. So now we know that the limit of f of x as x approaches plus or minus infinity is equal to 1. So this, in this case, is our horizontal asymptote. So now we know the following. As x approaches plus or minus infinity, y is approaching 1. And what that means is that as x begins to continue to grow either in a negative direction to infinity or a positive direction to infinity, that function is trying to reach the line and touch the line y is equal to 1, but it will never be allowed to touch it. It will continue to try to get closer and closer enough to try to actually finally land on it, but that will never happen. So in this case, for this particular approach where x goes to infinity in the negative direction or infinity in the positive direction, that function is trying to approach the line y is equal to 1. So now, after using all of our tools, we are now able to graph this function. So as you see here, we have the vertical asymptote, which is x equals 5. We drew that in. We have the horizontal asymptote of y is equal to 1. And now here we have the whole at 0, -1, because from the original function, we know that the original function is undefined at x equals 0. So that's an open hole. And we also found that the y-intercept, or the x-intercept, is -5, 0. So from the simplified factored form of f of x, we saw that the x-intercept is -5, 0. Then we also saw that as x goes to negative infinity, that function is trying to approach y is equal to 1 as graphed here. So as we come in from the point of discontinuity on the y-axis and allow x to travel out to infinity in a negative direction, this function is going to continue to rise and get closer and closer to y is equal to 1, but it will never get there. Then, as we go from the point of discontinuity on the x-axis, and as we travel to the right, we begin to see that as the values of x get closer and closer to that vertical line, x equals 5, y is approaching infinity in a negative direction, and it's ever trying to get as close to that vertical asymptote. Then here, as we jump over the vertical asymptote, we see that from our analysis, we discovered that as the x values approach 5, from the right, the y values are approaching infinity. And then here we also saw, once again, that as x approaches positive infinity, y is trying to approach 1. So here is the graph that we were able to use. Now problem 2. We're given that f of x is equal to x squared minus 4 divided by 2 if x is not equal to 2, and it's equal to 5 if x is equal to 2. So those are our two conditions. We have two separate conditions that when x is equal to 2, they've defined the output value for that function to be 5, or the coordinate 2, 5. Other than that, when x is not equal to 2, then you can use this expression, x squared minus 4 divided by x minus 2, to generate all your other values. Well, in this problem, we will be using the definition of continuity to examine this function. Step 1. Is f of x defined at x equal 2? Well, yes, it is. From our given conditions, we were told that when x is equal to 2, f of x, or y, is equal to 5. So to answer that question, yes, f of x is defined. It is defined at x equals 2. It has a real value, and it becomes the coordinate 2, 5. 2, 5 is part of the graph. Step 2, we must determine if the limit of f of x as x approaches 2 exists. We were given the original function f of x equals x squared minus 4 divided by x minus 2 as long as x does not equal to 2. We cannot use the original function to analyze and evaluate the left-hand and right-hand limits of f of x as x approaches 2 because it becomes an undefined function as x approaches 2 from the left and as x approaches 2 from the right. We do observe that the numerator of this rational function contains x squared minus 4, which is a difference of 2 squares. That is in the following form. A squared minus b squared is equal to a minus b times a plus b. So we can factor x squared minus 4 into the following factors. X minus 2 times x plus 2, because both x squared and 4 are perfect squares. So now we have the factored form of x squared minus 4. We rewrite f of x as follows. F of x is equal to x squared minus 4 divided by x minus 2. Now, in place of x squared minus 4, we substitute its equivalent factored form of x minus 2 times x plus 2, all over x minus 2. Now, upon looking at this in its factored form, we see that f of x has x minus 2 as a common factor in the numerator and the denominator. Notice I have x minus 2 times x plus 2 in the numerator divided by x minus 2. Well, directly looking at this, remember these expressions represent any type of number. So they represent a number, so they are common factors. So the x minus 2's, they divide one another out. So again, the x minus 2's divide into one another once. So as is shown here, the common factors of x minus 2 are dividing one another out. They're canceling one another out because they divide, because they're common factors. And now the function has been simplified to x plus 2. So this is the factored and simplified version of the original function of f of x. This function we can use, but it is not the controlling function. The original function is always, 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 always the controlling function. But we can now use this one to graph it because we've already taken care of the discontinuity when x is equal to 2. So now we have the function in its factored form, f of x equals x plus 2. We can use this factored version of f of x to analyze the left-hand and right-hand limits. So the limit of x plus 2 as x approaches 2 from the left, and now remember we can just go ahead and substitute the 2 into this expression now, and we end up with 2 plus 2, which is 4. So the limit of x plus 2 as x approaches 2 from the left is equal to 4. And the limit of x plus 2 as the values of x approach 2 from the right is equal to 4 as well. So now we've shown that now, since we see that the limit of f of x as x approaches 2 from the left is equal to the limit of f of x as x approaches 2 from the right, we can now say that the limit of f of x as x approaches 2 is equal to 4 because both the left-hand and the right-hand limits are equal to 4. And please remember this, in order for a limit to exist at a point, it cannot have two different limits at the same time. If that occurs, then the limit of the function at that point does not exist, because it cannot have two different limits at the same point at the same time. So now we've seen that the left-hand limit is equal to the right-hand limit. So we can conclusively say from our analysis that the limit of f of x as x approaches 2 is equal to 4, and it does exist. Step 3. Well, we saw that from step 1 and 2, in step 2, going backwards, we saw that the limit of f of x as x approaches 2 is equal to 4. And in step 1, we saw that when x was equal to 2, the functional output was defined to be equal to 5. Well, in this case, the limit of f of x as x becomes increasingly closer to 2 is not equal to f of 2, where it's defined to be 5, because 4 is not equal to 5. So as a result of that analysis, we can now say that f of x is not continuous at x equals 2. So it fails the third check. So this shows us that since the limit is not equal to where the function is defined, the function is discontinuous at x equals 2. Now we can go ahead and graph that linear equation, which is x plus 2. So when x is 0, y is 2. When x is negative 2, it's 0. Then when we put in 2, we get 4. But remember, in this case, that is a removable discontinuity, because it does not exist at that particular point when x is equal to 2. And we were given that when x is 2, it's defined to be 5. So this is the graph of that function. Thank you for joining me. This has been your teacher and your instructor, Mr. Joshua Davis. Please let me know if this instructional video on continuity was of help to you. Thank you, and have an excellent and fantastic and outstanding day.